Okay, so we left off where we were looking at example 4.3. We did part A, and now we need to look at part B. And so we're starting out with lithium chloride and silver acetate. So, let's see here. All right, so here we go. So we're lithium chloride and silver acetate. So we're writing the formula for lithium chloride, LiCl. Lithium's +1, chlorine's -1. And then silver acetate, so silver is +1, acetate's -1, C2H3O2. And so when we react these guys with predicted products, lithium's going to react with acetate, so we're going to get acetate. Lithium's +1, acetate's -1. Silver is going to react with chlorine to form silver 1 chloride, so AgCl. And then we have to predict the states of matter. So here, acetates are soluble in water. Chlorides are soluble. Halides are soluble in water, except silver, lead, mercury. And here we have silver. So this is an exception. So that's why our silver 1 chloride is a solid. So this is a balanced equation. So I didn't have to write any subscripts here. And so everything is balanced. Now I need to break apart my aqueous species into ions. Okay, so I do that. So lithium becomes lithium plus, chlorine becomes chlorine minus, silver plus, acetate minus, and then lithium and acetate again. And then the silver chloride, of course, stays together because it's a solid, it's a precipitate in the solution. And so I get rid of my spectator ions, I get rid of the lithium on both sides and the acetate on both sides, and I'm left with silver ions and chlorine ions reacting to form a silver chloride, silver 1 chloride solid. So that is my net ionic equation, okay, for those reactants there. And then finally, the last question for that example, we're starting out with lead nitrate, lead-2 nitrate, and ammonium carbonate. All right, so lead is Pb, nitrate's NO3 with a -1 charge. Since this is lead-2, I need 2 nitrates to balance out the charges there. Ammonium is NH4+, carbonate is CO3 -2. So I need 2 ammoniums to cancel out the -2 from the carbonate. Okay, and then now I need to predict the products here. So again, the outsides are going to react. So potassium and carbonate are going to react. I'm sorry, I said potassium. I meant lead and carbonate are going to react. And lead is going to be +2 and carbonate's -2, so it's going to be PbCO3. All right, and then my ammonium, NH4+, is going to react with my nitrate, NO3-. And because they're both +1 -1s, we don't have to add subscripts there. All right, so now I need to predict the states of matter. And so we know that carbonates generally are soluble. Exceptions are silver, lead, mercury, calcium, strontium, barium. And so here we have lead here, so it's going to be an insoluble compound. And then, of course, nitrates are always soluble, so that's aqueous. All right, so here we have our precipitate is formed. So now we need to go and make sure that everything's balanced. So here I have 2 ammoniums, so I have to put a 2 there. Okay, now I have 2 nitrates on the right-hand side as well. I had 2 originally. So now we're balanced. Okay, so moving on to the ionic equation. Again, we're going to separate out our aqueous species into ions. Okay, so we do that for each aqueous species. Okay, the lead-2 carbonate stays as a solid, and then of course the ammonium and the nitrate break apart. We get rid of the spectator ions in this example, and then we end up with lead and carbonate yielding lead carbonate solid precipitate. So that is our net ionic equation for our example 4.3. All right, so now let's see. Let's look at another reaction here. Here they have sodium chloride and silver nitrate. And so the sodium is going to react with nitrate. Silver is going to react with chlorine to form silver chloride. Silver chloride is soluble. It's a halide. Our halides are soluble except silver, lead, mercury. So here we have silver, so it's insoluble. Nitrates are always soluble, so other species is aqueous. And then, of course, you break everything apart. And so what ends up happening is your sodium is going to break apart to ions. Your chlorine's not going to, so it stays. And then your nitrate is going to be common on the other side too. So you're left with a net ionic equation of silver and chlorine forming silver chloride solid or precipitate. Okay, so the next type of chemical reactions we need to talk about are referred to as acid-base reactions. So next semester you're going to be dealing a lot with acid-base reactions, and that's in the case where you have a hydrogen ion is transferred from one chemical species to another. And we'll go through, next semester you're going to be going through, I think, 2 or 3 different definitions for acids, because one definition will not apply to every situation. Every will describe every acid out there. So anyway, starting at the most simplest definition for an acid is when a hydrogen ion is transferred from one chemical species to another. So what is an acid? It is a substance that will dissolve in water to yield hydronium ions. Okay, so believe it or not, water can actually react with itself. Okay, so when it does that, it forms hydronium ions. And so I'm just as a little side note here, I'm going to show you how that works. Now, this is at a very small amount. And, you know, we won't really talk about KWs this semester, but next semester we will. And so I thought I might just give you just an idea of what the hydronium ion really is. So we have liquid water that's able to react with itself. And so we don't have a single arrow. It's an equilibrium process here. And so what's going to happen is you're going to end up with what's called a hydronium ion. Okay, H3O plus and hydroxide ion. Alright, so the hydronium ion. So this guy is actually the chemical species that we refer to when we're talking about acids. Now, when we talk about acids, sometimes it's simplified. Okay, sometimes you'll see, like, maybe you'll see water broken apart into H plus and OH minus. Alright, you'll see it like that. This is sort of like how I was taught. And then, like, in reality, it's a hydronium ion. Okay, so this guy is really the hydronium ion. H plus really doesn't exist. It exists as a hydronium ion. Okay, so when I refer to H plus, be thinking hydronium ion. And just in case I'm not talking hydronium ion, that's really what it is. All right, so when we're talking about acids, they dissolve in water to yield hydronium ions. And so what's really interesting about strong acids, like hydrochloric acid is a strong acid. So what's special about hydrochloric acid? Well, 100% of the ions will be transferred over to water. Okay, so you see before how you got, if I show you here, I had a double-sided arrow there. And that's because this is an equilibrium process. This is not 100% yield on this side, and honestly, you hardly ever have 100% yield, but it's a double-sided arrow, meaning that reaction doesn't really go to completion all the way to the right-hand side. And so with strong acids, you notice there is a single arrow there because there is 100% completion with this reaction. That's why we refer to the acid as a strong acid. A strong acid will basically dissociate 100%. So the hydrogen ions are transferred from hydrochloric acid molecules to water molecules, creating the hydronium ion. So when we talk about acids, the hydronium ion is what we're talking about when we're saying that it's acidic, that the hydronium ion concentration is high. Okay, higher than hydroxide concentration. It's sort of like a balance. So we'll get more into detail about acids and bases. Here we're just trying to sort of give you a basic idea of what an acid is, and then we'll move on, and then later on we'll build upon that. So here we have two Erlenmeyer flasks, and here we have hydrochloric acid gas here, okay, and in water molecules. All right, so the hydrochloric acid dissolves in the water to become aqueous hydrochloric acid. Okay, so in the water it reacts as an acid, transferring protons to water molecules to yield hydronium ions. And so here we see the protons are being donated to the water molecules to form hydronium ions, H3O+, and then you're left with chlorine ions, Cl-, dissolved in water. And you can see how the water molecules are completely surrounding the Cl- because they're attracted to that negative charge on the chlorine, and you see how it's basically dissolving the Cl-. So virtually every HCl molecule that dissolves in water will undergo this reaction. Acids that completely react in this fashion are called strong acids. So you may be thinking, well, what's a weak acid? And so it's exactly the opposite. So a strong acid is going to react 100%. A weak acid basically will not react 100%. So it will do something less. And honestly, like weak acids usually do not dissociate hardly at all, or to a very small percent, maybe 5 or 8% versus 100%. So it's a drastic difference, and that's why we make that distinction. So with common strong acids, here we have hydrobromic acid, hydrochloric acid, hydroiodic acid, nitric acid, chloric acid, and sulfuric acid. I recommend you make sure you memorize these acids. Okay, there are only 6 of them. They're strong. And you don't have to memorize the weak acids list because, you know, if they're not on the strong acids list, guess what? They're probably a weak acid. All right, so there's a lot of different types of weak acids. So a far greater number of compounds behave as weak acids and only partially react with water. A large majority of the dissolved molecules remain in their original form, and only a relatively small amount of hydronium ions are generated. And so, like I was saying before, like acetic acid is usually like 5 to 8%. You know, it's nowhere close to 100%. And even if it were close, if it were like 90%, still would be considered a weak acid. So acetic acid, here we go. Only about 1% of acetic acid molecules are present in the ionized form. The use of a double arrow in the equation denotes the partial reaction aspect of this process. And so here we have the double-sided arrow, again, indicating that you have a mixture of reactants and products. So at this point so far, we've been assuming that we've only seen single arrows. And that indicates that the reaction goes to 100% completion. But in reality, especially when we're dealing with weak acids, at certain points in time, you're going to have a mixture of reactants and products. And it's going to be going back and forth and establishing what we refer to as an equilibrium. Okay, and so we'll learn more about equilibrium next semester. But it's basically a process where, you know, you don't have 100% products like you would if you were dealing with a strong acid. So there are a lot of different examples for weak acids and weak bases for that matter. So fruits such as oranges, lemons, and grapefruit contain citric acid. Okay, we know that's important for our health and maintaining our bodies. And vinegar contains acetic acid, and there's hydrogen ions during a acid-base reaction are highlighted in the inset molecular structure. So here we see the molecular structures for acetic acid and citric acid, and they're important parts of our daily lives are acids, and we end up consuming a lot of acids on a daily basis, especially if you like drinking soda pop, for example, is very acidic. Bases. A base is a substance that will dissolve in water to yield hydroxide ions. So we saw earlier how water reacts with itself to form the hydronium ion in hydroxide. And so hydroxides are sort of like the opposites of acids. And so the most common bases are ionic compounds composed of alkali or alkaline earth metal cations, group 1 and 2, combined with hydroxide ions. So for example, group 1 metals, sodium, lithium, potassium. Those are all all common bases: sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide as well. And so these bases are referred to as strong bases. So strong bases, just like strong acids, completely dissociate in water. And if they're not a strong base, then they're not going to dissociate 100% in water, and instead would dissociate to some partial extent. All right, so examples: sodium hydroxide, potassium hydroxide, barium hydroxide, calcium hydroxide, all strong bases. And so here's an example of sodium hydroxide breaking down into ions, sodium and hydroxide. Okay, so the dissociation process is essentially complete when sodium hydroxide is dissolved in water. All right, so the process of dissociation is a physical process. It's not an acid-base reaction. Okay, it's just sort of a breakdown of the strong base. So just like weak acids, weak bases produce hydroxide ions when dissolved by chemically reacting with water molecules, but just like weak acids, they don't react completely. They only react partially. Okay, so that's why they're called weak bases and not strong bases. A strong base would react completely 100%. Weak bases do not. They only will react to some extent less than 100%. So an example is ammonia. Okay, we use ammonia a lot in household products. It's very often found in those and fertilizers and things of that nature. And so ammonia here is here it's reacting with water to form the ammonium ion and the hydroxide ion. Of course, at this point we're talking about bases producing hydroxide ions, and the higher the hydroxide ions in the water, the more basic the water becomes. Okay, if you flip it the other way, the more H plus or hydronium ion concentration, when it gets higher, the more acidic the solution becomes. Okay, so with a weak base reaction, this is an acid base reaction, the protons is transferred from water molecules to the ammonia molecules. Okay, and so basically you're getting less H plus and more OH minus, and so the solution is becoming basic. So here's a couple pictures of showing you basic applications of using ammonia. Ammonia is a weak base. It's used in fertilizers. It's used in household cleaners like Pine Sol, Windex. It has that characteristic odor that some people think it smells clean, but you know, there's usually a lot of other reagents in there, so it doesn't. You don't have that strong ammonia smell that builds up, because that can be problematic because it can react with other things, other household cleaners as well. All right, so neutralization reactions. A neutralization reaction is a specific type of acid-base reaction in which the reactants are an acid and a base. Products are often sold in water, and neither reactant is the water itself. So when we have an acid-base reaction, your products are usually neutralized, and especially if you have a strong acid and a strong base, for example, you're going to have a solution, a product solution that has a pH value of roughly 7, and so it'll be completely neutralized, and so basically the acids will cancel each other out, and then you end up with a neutral pH solution at the end. And so here, that's what we're seeing. We have an example of magnesium hydroxide reacting with hydrochloric acid. And so you get magnesium chloride and water. Okay, so magnesium chloride is a salt, and the pH of this is going to be roughly 7. Now, next semester we'll actually talk more about neutralization reactions. Some reactions, like for example, if you have a strong acid and a weak base, you're going to have that strength of the acid that's going to be left over, and that's going to affect your pH. And we're going to learn how to calculate pH values after you have either a strong acid, weak base, or a weak base, strong acid reaction that goes on, and you're able to see the pH values that result from that reaction. In this case, because they're both strong base, strong acid reaction here, you get complete neutralization, and so you have end up with a pH of roughly 7, which is a neutral pH. So here we see a picture of a neutralization reaction taking place between citric acid. It's in the lemons in the basic part of the fish flesh. Okay, and so that neutralization process is what gives people enjoy the I guess the flavor of that, more of a neutralized dinner instead of having a fish that maybe has a very strong taste to it. The acid can sort of help alleviate that problem. All right, so we've talked about precipitation reactions. We've talked about neutralization reactions, which involve acids and bases. And so now we need to do a couple of examples here. And then we'll move on to what's called redox reactions, or oxidation reduction reactions. And so before we get to that, though, I want to look at some couple of examples in your book here where they're wanting us to write equations for acid-base reactions. And so all we're having to do is write a balanced chemical equation for the acid-base reaction described here. And so again, they're starting out with words. Okay, so the first part here, it says a weak hydrogen hypochlorite reacts with water. So we need to go ahead and write those words and write chemical formulas for those words, and then predict the products for those. Okay, so here, here's the question again. Let's see if that'll help a little bit. All right, so here's example 4.4. It says write balanced chemical reaction. So we're starting out with a weak acid, hydrogen hypochlorite reacts with water. So this is hydrogen hypochlorite. Hypochlorite's OCl minus, and so HOCl. Okay, aqueous plus water, liquid. Okay, and so how does this react here? Well, here we have a compound. I have two different compounds, and so my water is going to react with hydrogen to form the hydronium ion, and we're left with OCl minus. So here, if you think about it, this hydrogen hypochlorite is an acid, right? It's an acid that's donating its proton to water to form the H3O plus ion, all right? So by definition, this is acting as an acid. It's donating its protons to water to yield a hydronium ion. All right, so our reaction's balanced, so that's all they're looking for, is just being able to write a complete and balanced chemical reaction with an acid and a base. In this case, water is acting as a base. It's accepting a proton. All right, so for part B, it says a solution of barium hydroxide is neutralized with a solution of nitric acid. So barium hydroxide is BaOH, and then there's, because barium's plus 2, you need 2 hydroxide ions, because each hydroxide ion is -1. And then you have nitric acid, which is HNO3. Okay, so when we do our reaction here, the outsides react, the insides react. We have barium nitrate and HOH, or water. Okay, and then balancing out our charges here, barium's plus 2, nitrate's -1. So I need 2 nitrates in order to balance out the plus 2 of barium. And then water here, of course, we're having to balance out the number of elements we have on both sides. We're having to balance out our reaction. So we have barium on both sides. We have 2 nitrates here. So I have 2 there. We have 2 hydrogens plus 2. So that's 4 hydrogens. So I have to put a 2 here to make 4 hydrogens there. And so I have 2 oxygens plus 3 times 2, which is 6. So 6 plus 2 is 8. 8 oxygen on the right-hand side. And then I have 2 times 3, or 6 oxygen plus 2. So that's also 8 oxygens on the left-hand side. And so now my equation's balanced. And this is just showing you a neutralization reaction where we have a strong base and a strong acid reacting to produce water and barium nitrate, which is salt. All right, so now that we've kind of done that, we can actually move on to what's called redox reactions. Okay, redox reactions. And so redox reactions are reactions where that involve electrons, okay, transfer of electrons. And so in order to be able to see the transfer of electrons, we have to really learn about oxidation numbers. So that's what we're getting to. Now, the good news is that you guys have actually sort of have an idea, should have an idea about oxidation numbers, because we've already kind of used them when we were trying to write chemical formulas given the name of a species. So, for example, let me go ahead, going back to here. Let's say we have let's say we had sodium, like we just did some, right? Like sodium sulfate, like they both react, but you're having to balance the charges out. So sodium's +1, sulfate's -2, so you put a 2 there, and now you have sodium sulfate and it's balanced, right? So these numbers here, of course this is the charge on the ion, but like for example, sodium is group 1, so it's +1. Magnesium is group 2, so it's +2. So a lot of the stuff we've already learned about memorizing the ions that are going to be formed by certain elements. Those are part of the oxidation number rules. Okay, so we already kind of know a little bit about that. We're just going to have to again expand upon what we've already learned in order to learn more. All right, so with oxidation numbers, the first thing we have to really do is break apart each segment of the chemical equation so that we can actually really see what's going on, okay? And so we break the individual reaction into what's called a half reaction, okay? So a half reaction is basically we're singling out one element here, okay? And then we're taking a look to see actually what's going on. Okay, so here we can see sodium solid is going to break apart into sodium plus, and then chlorine gas is going to form chlorine minus ions. All right, so when we're talking about sodium chloride solid, it's really an ionic compound, and so that's what you see here, the ions that will basically can break apart. So we know sodium is a group 1 metal, so metals lose electrons, and chlorine is a nonmetal, and nonmetals tend to gain electrons. So there's for redox is RE stands for reduction, or I'm sorry, RED stands for reduction. OX stands for oxidation. So that's sort of a little what we call instead of saying oxidation reduction reactions, we just call them redox reactions. It's sort of like a nickname. And so oxidation is a loss of electrons, reduction is a gain of electrons. All right, so I have a fast way of memorizing that. I'm from Louisiana. In Louisiana, we have a lot of oil rigs. So if you remember the acronym oil rig, so O, oxidation is loss, and reduction is gain. And then we're, of course, referring to what? Electrons. Okay? All right, you don't have to put this part in there. Oil rig. Oxidation is loss, reduction is gain. Okay? So, gain of electrons is reduction. Oxidation is loss of electrons. All right. So, going back to our slides here. So, if we go back to sodium, we can see sodium's going from an oxidation number of 0 to +1. So it lost an electron, right? For each atom, it lost an electron. And then for chlorine, it went from 0 to -1. So it gained an electron for each atom. Okay? So sodium was oxidized and chlorine was reduced. So that's the whole point in breaking this reaction into half reactions, is sort of to isolate the oxidation numbers on each element to figure out which one's being oxidized and which one's being reduced. Okay, if one's being oxidized, the other one generally has to be being reduced. All right, so here's the part where students get kind of confused. So it's sort of like when we talk about reducing agents and oxidizing agents, it's the opposite of what we just said. So sodium functions as a reducing agent, a reductant, because it provides electrons or reduces chlorine. So basically, because sodium is a reducing agent itself, it was oxidized, but it reduced the other guy. Okay, so when you're talking about oxidizing or reducing agents, it's the opposite of what the species has done itself. So for example, chlorine is an oxidizing agent. Chlorine, of course, was reduced itself, but it was an oxidizing agent because it oxidized the other guy, right? The other guy became oxidized, so it's an oxidizing agent. So it basically removes the electrons, was able to remove the electrons from sodium. Okay, so it's an oxidizing agent. So when you think about reducing and oxidizing agents, it's usually the opposite of what you're looking at, or you're focusing, because it's basically doing the opposite operation. This is with respect to the other species. All right. So oxidation reduction reactions, some redox processes do not involve the transfer of electrons. So the product of this reaction is a covalent compound, so the transfer of electrons in the explicit sense is not involved. All right, so here we have an example of, we have hydrogen gas and chlorine gas. They have oxidation numbers of 0. And then here we have HCl, and this is a covalent compound, so you're not going to have charges associated with the molecules because it's a sharing of electrons, and it's not a transfer of electrons. Remember, you only get a transfer of electrons when you're talking about ionic compounds. So the oxidation number or oxidation state of an element in a compound is the charge its atoms would possess if the compound was ionic. All right, so here we have rules for assigning oxidation numbers. The oxidation number of an atom in an elemental substance is 0. All right, that's the first rule. The second rule, the oxidation number of a monatomic ion is equal to the ion's charge. All right, so let's look at a couple examples of the first and then the second rule. So the oxidation number of an atom of an elemental substance is 0. So for example, if I have a diatomic molecule like Cl2, okay, CO2 gas, its oxidation number is 0, so I'm going to put a little 0 there, okay, above it. It has an oxidation state of 0. All right. Then the second rule says a monatomic ion is equal to the ion's charge. This is rule 1. Rule 2, monatomic ion. So monatomic means one atom. So for example, if I have sodium plus, okay, monatomic ion. So one atom, it's an ion, it has a charge. So its oxidation number would be the charge of the ion itself, which is positive 1. All right, so that would be its oxidation number, plus 1. Okay, if I have O2 minus, all right, O2 minus, so it's a monatomic ion. Its oxidation number is going to be 2 minus or minus 2 for O2 minus. All right, if I have just iron by itself, iron solid, it has an oxidation number of 0. Okay, it is a neutral element. Okay, there's no charges there. And so it would just have an oxidation number of 0.